So we can't hear this. It's going. I haven't turned it on yet. When I do, it's going to blast out a 65 kilohertz beam. Because the wavelength is so small, it doesn't spread. Because 65 kilohertz has a wavelength like that. So it's going to be, in that sense, similar to a laser. It just comes right out as a beam. Now, how do we make that audible? Well, they put a modulation on top of the 65 kilohertz. There's a modulation. And now, here's the next thing I have to tell you. That 65 kilohertz is very high amplitude. It won't hurt you, we don't think. Okay? You certainly can't hear it, and we don't think it'll hurt you. And it's very high amplitude. And what happens when you have two sound waves like this, sound plus sound can create sound, but only at high amplitudes. At low amplitudes, sound waves just travel right through each other. You may be sort of familiar with this. But at high amplitude, you can create sound. So what happens in this apparatus is the audio sound, the sound that you're going to hear, is actually created in the beam, not here. And because it's created in the beam, and it stays in the beam, we have a beam of sound. So let me demonstrate this for you. Let me turn it on. And I'm going to find the piece of music that we like.
Yeah.
You may not like it.
The Eagles? You like the Eagles? Okay, good. Oh, we have a friendly audience this year.
Yeah. I think they're just saying that to make us feel better.
Right. All right.
It's worth the $2,000. It's not our money. Now, the sound that you're hearing is being created in this beam. It almost sounds like it's coming from your head. So let me try to scan the whole audience so everybody gets to hear this. Absolutely remarkable. Pete, are you getting it? Let's try to, one more thing. Let's try to bounce it off the wall. Raise your hand if you can very clearly hear it. I'm going to try to bounce it off the wall. Look at where the hands are raised. It's